Hello, welcome back to the NPTEL online certification course on deep learning. In today's lecture, we are going to talk about the semantic segmentation problem, and we have said earlier that for coming few lectures, we'll mostly concentrate on applications of the deep learning techniques that we have done so far. In our previous class, we have talked about the deconvolution and the upsampling operations or unpooling operations. So, what we said is for this kind of application, say semantic segmentation, where the operation you have to do on every pixel level, or for every pixel you have to take a decision that to which of the classes the pixel belongs to. So, in order to have such a decision, what is required is the abstraction of your input images, which is given by the convolution layers. I have to blow it up to the size of your input image, and for that the kind of operations which are required is upsampling or unpooling, and then we have to have the operation of deconvolution, which is the reverse operation of convolution, which is done in the forward direction. So, in today's lecture, we will talk about the semantic segmentation problem, and we will try to discuss two particular approaches for semantic segmentation. One of them is called fully convolutional network based semantic segmentation, and the other one is deconvolutional network based semantic segmentation. So, before going to the problem of semantic segmentation, or how to obtain semantic segmentation of and given image using either fully convolutional network or using a deconvolutional network, let us see what is meant by image segmentation and what is semantic segmentation. So, you see that image segmentation is basically a process of partitioning an input image into different regions, and this partitioning is done based on certain characteristics of the input pixels. So, you partition the image in such a way that in every partition or every region within that image, if I take 2 pixels, then the characteristics of those 2 pixels will be very similar. Whereas, if I take 2 pixels from 2 different partitions or 2 different segments, then the characteristics of those 2 pixels or the characteristics of those 2 pixels are likely to be very different. So, based on similarity of the characteristics of the pixels and sometimes based on connectivity as well, you partition the image into different regions, and each of those regions is known as a segment. The purpose of this segmentation is that you can identify or you can group together the pixels belonging to a particular object or the pixels belonging to a particular class. That class may be, say, buildings, the class may be persons present in the image, the class may be cars, the class may be cow, anything. But what is expected is when I take 2 pixels belonging to a car, then the characteristics of the region around those 2 pixels, they will be very, very similar. So, as shown in these figures, you find that in the top left corner image, you have 2 persons, and the next 2 images in the same row as well as the image below it that identifies the regions or the pixels belong to those persons. Particularly in this particular case, you find that in this particular image, you find that you don't have any differentiation between whether a pixel belongs to a hat of the person which the person is wearing, or it belongs to the body of the person. Similarly, there is no demarcation between this person and this person, though there are 2 different persons. So, it says that these pixels belong to region or the region is occupied by persons. Whereas, if you look at this, you find that this is the hat region and this is the body region, where there is some demarcation, though all these pixels belong to different persons, but within the persons there is further subclassification. Similarly, if you come over here, there is an aeroplane, and here you find that it has grouped all the pixels which belongs to the aeroplane. So, depending upon the characteristics that we want to extract and the way we want to use those characteristics for segmentation purpose, we can have two different types of segmentation operations. One of the segmentation operation is what is known as semantic segmentation, and the other kind of segmentation operation is what is known as instance segmentation. So, let us see that what are these two types of segmentations. So, firstly, let us talk about what is semantic segmentation. Semantic segmentation is the process which links each pixel in an image to a class level. Say for example, within an image I have 5 different cars, right, and the car is one of the classes which is present in the image. Similarly, in the same image I can have buildings, and building is another class. In the image I can have different persons, and the persons or the man or human being, they become another class. So, I can have an image where in the image I have 3 different classes or 3 different classes of objects. One class is car, one class is building, one class is say persons, another class maybe is a signboard, road sign, and many such things. So, in case of semantic segmentation, it simply says or associates a pixel within the image to a particular class. So, it simply says whether a pixel belongs to car, it does not identify which car it is, or a pixel belong to a person, or a pixel belong to a building, or a pixel belong to a signboard, and all that. But it does not differentiate. If there are multiple instances of the cards, semantic segmentation does not tell you that to which of the cards a particular pixel belong. Or in other words, what we can say is that all the pixels belonging to a particular class forms a semantic segment. Okay. Or in case of semantic segmentation, we don't have any boundary of the different instances of the objects belonging to the same class. Whereas, if we talk about say instance segmentation, say for example over here, you find that we have shown 2 different segmentation output of an image, where within the image there are say 5 persons present within the image, right. So, if you see the image which is the segmented output, which is shown on the left, say this one, here you find that all the pixels belonging to the persons have been classified into the same class, that is a person class. It does not say that which pixel belong to which of the persons. Whereas, if you look at this particular segmented output, here you find that in addition to classification, it also tells you the boundary of different persons. That means every instance of an object belonging to that class has been segmented out separately. So, this first kind of segmentation, the segments that you obtain, this is what is known as semantic segmentation, which simply tells that the pixel belongs to which class, and this kind of segmentation is known as what is instance segmentation, where it does not only tell you which class, but it also identifies that to which instance of that class a pixel belongs. So, this is the difference between your semantic segmentation and instance segmentation. So, in our lecture today, in today's lecture, maybe in the next lecture as well, we will talk about the semantic segmentation problem, and we will see that how this semantic segmentation problem can be solved using deep neural networks. So, now let us see that what are the applications of such semantic segmentation. You take for example, navigation or driving of an autonomous car. So, for an autonomous car, when it is navigating in a particular region or it is navigating on a road, the car has to know its surroundings. So, car has to know that which pixels belong to the road, so that the car will move on the road only, it does not hit a building. And in order to avoid hitting a building, the car has to know that which are the pixels which corresponds to buildings. If there is pedestrian moving around, the car also has to know that which are the pixels which identifies the pedestrians which are moving around, so that the car does not hit a pedestrian. So, this semantic segmentation of the scene is a very important aspect of an autonomous car navigation problem. Similarly, the semantic segmentation can also be used in medical applications. So, this is slide shows a slice of a brain MRI. So, a radiologist or a doctor may like to know that what is the extent of white matter, what is the extent of gray matter, or what is the extent of cerebrospinal fluid present in the brain. And for this purpose, this semantic segmentation, which identifies the regions which belong to white matter or identifies the regions which belong to gray matter, similarly identifies the regions or the pixels which belong to cerebrospinal fluid. This information is very important for diagnosis. So, the semantic segmentation plays a very important role for such medical applications as well. So, these are just two different applications that I have highlighted, but semantic segmentation has many more applications, right? In wherever we think of application of computer vision, for example, if I want to have an automated assembly shop, or say robot navigation, robotic vision, in all cases the robot may have to identify a particular object or a set of objects which are present in the shop floor. So, semantic segmentation for identifying objects, this plays a very important role in machine vision applications in industries. So, given these two applications, now let us come to an approach of fully convolutional network or fully convolutional neural network used for semantic segmentation purpose. So, the work that I am going to present here was published in was presented in CVPR 2015 by persons Jonathan Long and the colleagues. So, earlier we have seen the convolutional neural network or deep convolutional neural network, and we have seen that whenever you have a deep convolutional neural network, the deep convolutional neural networks are basically used for classification or recognition purpose. So, there we have a convolutional layer, then you have max pool layer, you have convolution layer, max pool layer appearing one after another, where the convolutional layer actually extracts the features from the input images, or it extracts some abstract information from the input images, and layer by layer the convolution networks actually gives you the information at different layers of abstraction, different levels of abstraction of the input signal that you have provided, that you want to classify. The purpose of max pool layers, we said that the max pool layer tries to find out that which particular feature has got the prominent activation or prominent response, the maximum response to a given filter in a given region, which is known as receptive field. And based on this, what the max pool layer does is it takes a max pool window, and from that window it simply extracts the maximum activation, and that maximum activation is passed to the next convolutional layer for further processing. So, in the process, the max pool layer identifies the maximum activation, and also it reduces the dimensionality of the feature maps. That helps in processing because your computation goes on reducing as the dimensionality of the feature maps reduces. So, as a result, as you move along the convolutional layer from say shallow layers of the input layer to the deeper layers or the output layers, your information abstraction level goes on increasing, or in other words we can say that every feature gets a global information within the receptive field of that particular node. But in the process, what you lose is the locational information, because if I take a particular feature in a feature map in a deeper layer, the receptive field of that particular node when I come to the input layer is very large. So, you get the global information of that large receptive field, but at the same time in which area within this receptive field your filters give maximum response, that is lost. So, what you get is you get the informations at different levels of abstraction through these convolution operations and the max pool operations. And we have seen earlier that the outer layer or the final layer or few layers at the final levels, they are known as fully connected layers. And these fully connected layers are just similar to the multi-layer perceptron which are used for classification or recognition purpose. And this fully connected layer or the output of the fully connected layer actually tells you that to which of the category or to which of the class your input signal is classified. So, such a network is shown in this part of the figure. So, this is what is that convolutional network, followed by here what we have is a fully connected network. So, these convolution networks actually gives you the feature map, and finally the feature map passes to the fully connected layer, and the output of the fully connected layer is a decision about to which of the category or to which of the classes your input image belongs. So, here you find that this particular output which shows that this input image actually belongs to a category of a cat. Now, in fully convolutional layer, which these Jonathan Long and others have reported, that they have said that okay, instead of considering the output layer as a fully connected layer, what happens if we consider this to be a convolutional layer as well? So, there is nothing wrong. I can consider this output layer, which is otherwise a fully connected layer, to be a convolutional layer. And if I consider this to be a convolutional layer, in that case you find that every node in this final convolutional layer has a receptive field which is the entire feature map being fed to this particular layer. Okay. So, and if I consider this to be a fully connected layer, then I can simply blow up the outputs of this fully connected layer in the form of a feature map, and that feature map looks like this. So, here in the fully connected layer, if there are say 1000 nodes, I can blow it up in the form of an image, where image will be of size say m by n depending upon the number of nodes that I have in the fully connected layer. And if you look at this, that this feature map that you get, that gives you some sort of heat map of the cat, or this region in this particular feature map. This shows that in this region I have this particular object which is the cat. But the problem here is, as the information has flown through a number of convolution layers and the number of max pool layers, so the size of the feature map that you get over here is much less than the size of the input image which is actually fed. So, in order to have the pixel wise decisions, that is to take a decision at every pixel whether the pixel belongs to the cat or the pixel belongs to something else, I need to blow up or expand this image to a size which is of same size as that of the input image. So, the way it has been done or reported in this work is something like this. So, if you look at the entire flow of the convolutional network, in this convolutional network you find that there are 7 different convolution layers. So, these layers are as shown over here. So, I have an input image. Suppose the input image is of size m by n. Then you have the first convolution layer followed by a pooling layer. So, this pooling layer, if the pooling window is 2 by 2 and with stride 2, then after pooling the size of the image which will be fed to the second convolution layer will be m by 2 by n by 2. So, you find that the image size simply becomes half. Similarly, the feature map, size of the feature map which is fed to this convolution 3 is m by 8 by m by 8, or it is reduced by a factor of 8. Similarly, after pool 3 it is reduced by a factor of 16. After pool 5 it is reduced by a factor of 32. So, if my original input image was of size m by n, the size of the feature map that you get after this convolution layer 7 is reduced by a factor of 32. So, because of this, if I want to get a pixel level decision, that means for every pixel I have to decide whether the pixel belongs to cat or the pixel belongs to something else, what I need to do is I have to expand or blow up this feature map by a factor of 32. So, for that what I have to do is upsampling by a factor of 32, and this upsampling concept we have discussed in our previous class, that what I can do is I can go for deconvolution with a deconvolution filter with a larger stride greater than 1. So, if you perform a deconvolution operation with stride greater than 1, your output map that you get is larger than the size of the input map. The other operation that we have discussed is that you perform the deconvolution, which we said it is sub-pixel convolution. So, in sub-pixel convolution what you have done is that you have expanded or upsampled the feature map, and all the intermediate regions you filled up with 0. So, it is what is known as 0 upsampling, and after upsampling the feature map what you have done is you have performed the deconvolution using the deconvolution kernel. And we have seen that this deconvolution kernel has certain parameters, and these parameters are actually learnable parameters. So, you learn these parameters, or the network learns these parameters during the training operation following the back propagation algorithm or gradient descent algorithm. So, we will talk about how to train such networks maybe sometimes later. So, here what it's shown is that what I want to do is, so at this particular point whatever is the size of the image or size of the feature map, I know that the size of this feature map is 1 by 32 of the size of the original image. So, what I have to do is I have to blow up this size to 32 times, so that our output image matches with the input image, and then every pixel within this output image has to be classified to one of the classes which are actually present within this image. So, for this classification purpose we have to train this particular network, and as I said that I will come back to the training of this network a bit later. So, when you go for this upsampling by a factor of 32, this can be done in various ways. We can perform the upsampling in a single shot operation, that is upsampling by a factor of 2, and then after upsampling you go for deconvolution operation using the deconvolution filter or deconvolution kernel. But the problem in that case is that if you are going for upsampling in a single step, then your upsampled image or the map that you get will be very sparse, and the segmentation output that you get may not be very proper. So, the other way in which the same can be done is that you go for multiple steps, and here you use the concept of skip connection. So, what you do is you take the output from pool step 5 in the convolutional part, and you upsample it by a factor of 2. Similarly, take the output from pool 4 in the convolutional network after max pooling operation, and then you upsample by a factor of 4. So, you find that output of pool 5 upsampling by a factor 2 and output of pool 4 upsampling by a factor 4, here the size of the two maps that you generate the match. And then what you do is this upsampled version and this upsampled version, you simply add them together. And after adding them, you again upsample it. So, this output is now 16 times upsampled from here. 16 times upsampled from the output of your final convolution layer. Next operation what you can do is you can take the output from pool 3, upsample it by a factor of 16, and this was already upsampled by 16. So, you upsampled it by a factor of 2. Just a minute. What we had done before is, if you come to this, after convolution 3, it was downsampled by a factor of 8. Here, it was downsampled by a factor 8 after pooling layer 3. So, from the output of the pooling layer 3, we have to upsample it by a factor of 8, and this one, the output that you get from here by combining these two, you upsample it by a factor of 2. So, both of them taken together are now upsampled by a factor of 32, upsampled by a factor of 8. So, you add them together. So, here you get what is the upsampled version by a factor of 8, and then you can combine these two together. So, whatever the sparse representation that you have got here by upsampling by a factor of 32 in a single step, now what you are doing is hierarchically you are combining with that the upsampled versions which are at finer scales. So, as a result, the output that you get, that becomes much better than the output that you get using a single step upsampling. So, now let us just see that what are the kind of outputs that you can have. So, here is the output. It shows that if this is the ground truth of your semantic segmentation, once you directly upsampled by factor 32, this is the output. This is what is FCN 16. Now, FCN 16 is output over here. This is what is your FCN 16, and this is what is your FCN 8. So, you find that in these two cases, your output of FTN 16 and output of FCN 8 is much better than output of FCN 32. So, this is much closer to your ground truth. This is over here. So, this is an approach where a fully connected neural network can be conceived as a fully convolutional neural network, and this fully convolutional neural network is used for the semantic segmentation purpose. So, we will stop here today. In our next class, we will talk about a deconvolutional neural network that can be used for semantic segmentation. Thank you.